Right now, a computer exists that could crack every password protecting your bank account, your personal data, and government secrets in just seconds. It could discover the cure for cancer, Alzheimer's, or the next pandemic in days instead of the decades we wait today. Problems that would take our most powerful supercomputers 10,000 years to solve, this machine does it in under 4 minutes. This isn't science fiction. Google, IBM, and Microsoft are pouring billions into quantum computing. The future is quantum, and it starts now. But how does this incredible technology actually work? Let me show you. Before we dive into quantum's mind-bending reality, let's understand how your regular computer actually works. Everything digital starts with something called a bit, the smallest piece of information your computer can understand. Watch this cube. It can only show 2 states, 0 or 1. Never both, never anything in between. Every photo, video, text message, and app on your phone, it's all just patterns of zeros and ones flowing through circuits. See these data streams? Your computer doesn't understand words or colors, it only speaks in binary. Everything gets translated into this simple language of on and off. Think of each bit like a light switch in your house. It's either on or off. There's no sort of on or halfway off. Just like these switches, each bit has exactly 2 possibilities. This limitation is both classical computing strength and its biggest weakness. Now imagine millions of these binary musicians, each playing only 2 notes. But together, they create the symphony of your digital world. Your smartphone coordinates billions of these on-off decisions every single second, creating everything from games to video calls. Modern processors flip these bits billions of times per second. Each particle you see represents thousands of calculations happening right now. It's incredibly fast, but still limited to checking each possibility one at a time. And that's where quantum computing changes everything. But what if we could break free from this binary prison? What if bits could be 0, 1, and something impossible in between? That's where quantum mechanics enters the story. Now here's where quantum computers blow our minds. Instead of regular bits, quantum computers use quantum bits, or qubits. Look at this comparison. Classical bits are rigid, predictable. They're either 0 or 1, period. But qubits? They're magical. They can exist in superposition, being both 0 and 1 at the exact same time. This isn't just theory. This is real quantum physics in action. Watch this qubit spinning in superposition. It genuinely exists in both states simultaneously until the moment we measure it. Classical computers check possibilities one by one. Quantum computers explore all possibilities at once. It's like the difference between walking through a maze and flying over it. Think of it like a spinning coin. While it's in the air, is it heads or tails? It's actually both. That's exactly how a qubit behaves in superposition. These spinning coins represent qubits maintaining multiple states simultaneously, something that seems impossible in our everyday world, but is completely normal in the quantum realm. This creates what we call quantum probability clouds. Instead of definite locations, qubits exist in clouds of possibility. We can't predict exactly what state we'll find them in, only the probability of each outcome. It's like having a computer that doesn't just calculate answers, it calculates all possible answers at the same time. And here's the mind-blowing part. The power grows exponentially. 1 qubit gives you 2 possibilities. 2 qubits give you 4. But 10 qubits? Over 1,000 possibilities processed simultaneously. 20 qubits can explore over 1 million states at once. This exponential scaling is what makes quantum computing revolutionary. But superposition is just the beginning. Wait until you see how qubits can become mysteriously connected across any distance. But wait, it gets even weirder. Quantum computers harness another mind-bending property called entanglement. Watch these 2 particles. When they become entangled, they form an invisible, instant connection. It's like they're having a secret conversation that defies everything we know about physics. Einstein himself was so disturbed by this phenomenon that he called it spooky action at a distance. He couldn't believe that particles could instantly affect each other, no matter how far apart they were. Einstein thought there had to be some hidden explanation, but decades of experiments proved him wrong. Picture 2 magical coins that are quantum entangled. No matter how far apart you separate them, when one coin shows heads, the other instantly, and I mean instantly, shows tails. It's not sending a signal, it's not communicating. It just somehow knows what its partner is doing. This connection works across any distance, even billions of light years apart. Information doesn't travel between them because that would take time. Instead, they share a quantum state that transcends space itself. Measure one particle here on Earth, and its entangled partner on the other side of the universe immediately responds. This quantum teamwork is what makes quantum computers so powerful. Entangled qubits work together as a synchronized network, processing vast amounts of information simultaneously. It's like having a team of workers who can instantly coordinate without ever talking to each other. So now we have qubits in superposition and entangled together. But how do we actually control and manipulate these quantum phenomena to solve real problems? So now we have qubits in superposition and entangled together. But how do we actually control these quantum phenomena? Just like classical computers use logic gates to flip bits, quantum computers use quantum gates to manipulate qubits. Watch this transformation. Quantum gates are like special filters that change qubits as they pass through. Meet the Hadamard gate, the superposition creator. Feed it a classical qubit in state 0, and it transforms it into a perfect superposition of 0 plus 1. It's like taking a coin that's definitely heads and making it spin in the air. Suddenly it's both heads and tails simultaneously. This is the C-No-T gate, the entanglement creator. It links two qubits together with that spooky connection we talked about. The control qubit tells the target qubit how to behave. When they pass through together, they become quantum partners, forever connected no matter how far apart they travel. Quantum computers have an entire toolbox of these reality-bending tools. Pauli gates for flipping states, phase gates for rotating probabilities, Toffoli gates for complex logic. Each gate performs a specific transformation. Together, they give us complete control over quantum information. And here's where it gets exciting. We combine these gates into quantum algorithms. Like following a recipe, we guide qubits through a series of transformations, step by step. Initialize, create superposition, entangle, rotate phases, and finally measure the result. It's quantum programming in action. But building these quantum algorithms requires some pretty incredible engineering. Let's see what actual quantum computers look like. Unlike your laptop, quantum computers are massive, room-sized machines that look more like futuristic art installations than computers. They're complex engineering marvels that require extreme conditions to operate. And I mean extreme conditions. Those qubits we've been talking about? They must be kept at near absolute zero, negative 273 degrees Celsius. That's not just cold, that's colder than the vacuum of outer space. Watch this temperature gauge drop. The quantum states only exist at these mind-boggling temperatures. But here's the problem, qubits are incredibly fragile. Any tiny vibration, electromagnetic interference, or heat can cause something called decoherence. Watch what happens. The quantum magic disappears instantly and your qubits start behaving like regular bits. It's like trying to balance a pencil on its point during an earthquake. Despite these challenges, we've achieved something extraordinary. Google's Sycamore processor reached quantum supremacy, solving a problem in 200 seconds that would take our most powerful classical computers 10,000 years. That's 50,000 times faster. This wasn't just an improvement, it was a quantum leap. And here's the amazing part. You can actually access these quantum computers today. Companies like IBM, Google, Rigetti, IonQ, and Microsoft offer quantum computing through the cloud. Real quantum computers, accessible from anywhere in the world. You can literally run quantum algorithms from your laptop at home. So what can these incredible machines actually do? Let's explore the mind-blowing applications that could change everything. So what can these incredible machines actually do? The applications are nothing short of revolutionary. In drug discovery, quantum computers unlock the secret language of molecules. They simulate how proteins fold, how drugs bind to cancer cells, how viruses attack our immune system. Diseases that have plagued humanity for centuries could meet their match in quantum-designed cures. Cybersecurity faces its biggest disruption ever. Current encryption that would take classical computers millions of years to crack? Quantum computers could break it during your morning coffee. But here's the twist. They also create the ultimate defense. Quantum encryption so secure it's protected by the laws of physics themselves. Artificial intelligence is about to get its biggest upgrade in history. Neural networks that currently take months to train could learn in hours. Pattern recognition that stumps today's AI becomes child's play. We're talking about AI systems that don't just think faster, they think in fundamentally more powerful ways. Materials science enters a new era where we become atomic architects. Instead of discovering materials by accident, we design them with precision. Imagine solar panels with perfect efficiency, spacecraft materials lighter than air but stronger than steel, batteries that charge in seconds and last for years. Financial markets transform into quantum-powered prediction machines. Portfolio optimization that currently requires overnight calculations happens instantly. Risk analysis across millions of scenarios completes before you finish reading this sentence. It's not just faster trading, it's seeing market patterns invisible to classical computers. These applications sound like science fiction, but there's a catch. Before you start planning your quantum future, we need to talk about reality. These applications sound incredible, but before you start planning your quantum future, we need to talk about reality. The biggest enemy of quantum computing isn't technology, it's physics itself. Any tiny vibration, heat, or electromagnetic interference instantly destroys quantum states. The quantum magic simply disappears, and your sophisticated qubits become ordinary bits. And then there are the errors. Quantum operations are incredibly delicate and fail constantly. Current error rates hover around 30%. Imagine if your smartphone failed 3 times out of every 10 operations. Classical computers need error rates below 0.1% to be useful. We're still 1,000 times too unreliable. Even when everything works perfectly, quantum states only last microseconds before collapsing. That's not enough time for complex calculations. While your laptop can process data for hours, quantum computers lose their quantum properties faster than you can blink. It's like trying to build a sandcastle during an earthquake. Here's the tough truth. Quantum computers are incredibly specialized tools. They're like Formula One race cars, phenomenally powerful for specific tasks, but you wouldn't use one for grocery shopping. They won't replace your smartphone, laptop, or gaming console anytime soon. They're built for narrow, specific problems only. We're still in the Stone Age of quantum computing. Today's quantum computers are like those room-sized machines from the 1940s, impressive engineering feats for their time, but nowhere near practical for everyday use. The quantum revolution is coming, but we're decades away from quantum laptops. But here's why none of these limitations will stop the quantum revolution. Scientists are developing quantum error correction. Imagine qubits that heal themselves when errors occur. By 2026, we'll see self-correcting quantum systems. By 2030, quantum drug discovery. By 2035, quantum AI acceleration. The timeline is set, and progress is accelerating. The applications emerging from labs today will transform every field of human knowledge. Quantum computers will revolutionize drug discovery, creating personalized medicines in days instead of decades. AI systems will leap beyond human intelligence. Climate models will predict weather patterns with perfect accuracy. The future isn't just faster, it's fundamentally different. The global quantum race is already underway. The USA invests $25 billion annually, China $20 billion, the European Union $12 billion. MIT, Oxford, IBM Research, Google AI, and Microsoft are building the quantum future right now. This isn't a distant dream, it's a present reality with massive resources behind it. A new generation of quantum programmers is emerging. Drag-and-drop quantum gate designers, real-time qubit visualizers, quantum debugging tools. Programming quantum computers will soon be as accessible as building websites today. Quantum IDE 2030 is already in development. The quantum workforce is being trained right now. Welcome to the quantum age, where quantum internet connects the globe instantaneously, where quantum AI thinks beyond human comprehension, where quantum medicine designs cures at the molecular level, where quantum materials engineer solutions to climate change. The future is quantum, and it starts now. So there you have it, quantum computing from basic concepts to limitless possibilities. We've journeyed from simple bits to mind-bending qubits, from classical gates to quantum entanglement, and from today's limitations to tomorrow's revolutionary breakthroughs. The key takeaways are clear. Quantum computers use superposition and entanglement to process information in fundamentally different ways. They're not better at everything. They're specialized tools for specific problems. And while we're still early in the quantum age, the potential is absolutely enormous. Think about it. Drug discovery at quantum speed, unbreakable quantum encryption, AI systems exponentially smarter than today, and perfect climate change modeling. These aren't distant dreams. They're coming within the next decade. Whether you're a student choosing a career path, a professional wondering about future disruption, or just curious about cutting-edge science, quantum computing is definitely worth understanding. The quantum future is coming, and now you're prepared for it. So here's my question for you. What quantum application excites you most? Is it drug discovery that could save millions of lives? Unbreakable encryption protecting our digital future? Or AI acceleration that could solve humanity's biggest challenges? Let me know in the comments below. And if this video helped demystify quantum computing for you, smash that like button and subscribe for more mind-expanding tech content. The future is quantum, and it's going to be incredible.